Hi all, this is Mr. Spurk, and we're just going to review some of section 8.2. This is where we started talking about Lewis dot diagrams. This is not the full notes or the full video from class. This is one that we did in class, so I didn't have a video, so I'm just going to do a very quick rundown of drawing Lewis structures so you can refresh for the summer assignment. So here's the steps to drawing Lewis diagrams. Remember, we arrange the elements how you think that they should be bonded, so you just write their symbols on the page. If there are only two atoms, we just place them right next to each other. Remember that two atoms that form a molecule are always going to be linear in shape because 2 points make a line. If there are more than two, you place the least electronegative or the most metallic in the middle. So remember, fluorine is the most electronegative element on the periodic table, so the one that is further away is going to go in the middle. Typically, this is going to be a carbon or a nitrogen atom. Hydrogen can never be in the middle. The reason for this is, remember that hydrogen only has one valence electron, so it can only ever bond with something one time. So it will never, ever, ever, ever bond more than once. If you ever draw more than a single bond to a hydrogen, you've made a mistake. So the first thing you're going to do is total all of the valence electrons. Remember that the group number equals how many valence electrons they have. So group 1 has 1, group 2 has 2. Jump over to group 13/3a. Those have 3, group 4, 4, and so on and so forth. Remember, if you're not following the 4a, 5a, 6a pattern, it's still group 14, 15, 16, and 17. And remember that it's always this number that tells you how many valence electrons that they have. So remember that those number of valence electrons is like how much money you have to spend, and you have to spend all of it. You can't spend more, you can't spend less. The first thing you're going to do is place the bonds as dashes connecting all the elements. Subtract that number of bonding electrons from the total number of valence electrons. And then the remaining number is the remaining valence electrons as dots that you have to place. And we want to make sure that we complete the octet rule. Remember that all elements have an octet of 8, except for hydrogen and helium. They have an octet of 2 because their first shell of electrons can only house 2 electrons. You're going to place those on the outer elements first and then go to the middle one. If there are still some left over, then you go to that central atom. Once they're all placed, you got to make sure that every element has a full octet, and then you know that you are good to go. So let's just start doing a couple examples. So hydrochloric acid. So first things first is I'm going to write down my two elements. So HCl, that's hydrogen and chlorine. Then I want to tally up my total valence electrons. Hydrogen is in group 1. Chlorine is in group 7. Total of 8 valence electrons. So I have to use all 8. Next step is to draw a dash connecting them. Remember that it takes 2 points to make a line, or 2 electrons to make a single bond. So there are 2 electrons there. Don't forget that. So I'm going to subtract the 2 that I've used. That tells me that I have 6 more to use. Then, if we follow the steps, they get placed around the outer elements. However, hydrogen cannot ever have dots on it. It can only ever have 2 electrons around it. And currently, it has 1, 2 electrons right near it that make up that bond. So those have to go to the chlorine. 1, 2, 3, 4, 5, 6. Now we check our octet. So if I look at my hydrogen, how many electrons are around it? 1, 2. That's good. Hydrogen has an octet of 2. Let's look at chlorine. How many electrons are around there? 1, 2, 3, 4, 5, 6, 7, 8. So hydrogen has its octet of 2. Chlorine has its octet of 8. We are happy. Let's go ahead and move on. Let's look at fluorine. With fluorine, we have 2 F's here. So F, F. We have 2 of them, so it's 2 times how many valence electrons they have. Fluorine is in group 7, so 7. Total of 14 electrons. Let's draw in my dash. Subtract those 2 that we just used. We have 12 left to place. We know that they go around the outer elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have used a total of 14 electrons, which is great. Now let's check that octet. We have 1, 2, 3, 4, 5, 6, 7, 8 electrons around that fluorine. And we go to this fluorine. 1, 2, 3, 4, 5, 6, 7, 8. He has 8 as well. Remember that they share these electrons here because this is a covalent bond, and covalent bonds are made by sharing electrons. All right, let's jump to ammonia. So we have multiple atoms here, so we need to decide what's our central atom. Remember, to decide your central atom, it's going to be the least electronegative, but the other rule is that hydrogen cannot be in the middle. So this has to be N with 3 H's around it. Remember, it does not matter exactly where your hydrogens are. If you, feel like you want to put your hydrogen up there instead, that's perfectly fine. I tend to put mine at the bottom. Tally all these up. Hydrogen has 5 valence electrons because it's in group 5. There are 3 hydrogens, and they each have 1 valence electron for a total of 8. Drawing my dashes. That used 2, 4, 6 electrons, because remember, it takes 2 electrons to make a single bond. We have 2 more left over. Typically, the rule says place them around the outer elements, but hydrogen cannot have more than 2 electrons around it. And currently, each hydrogen has 2 electrons around it, because remember that there are 2 in that bond. So they have to go to the central atom. 1, 2. Let's go ahead, count up, and make sure our octet rule is satisfied. This hydrogen has 1, 2. This hydrogen has 1, 2. That hydrogen has 1, 2. All of our hydrogens are happy. Let's check our octet. Sorry, guys. Let's check our octet for nitrogen. Circle all the electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. He is happy. So again, I drew it with all those bubbles around it. That's just for you guys to see the counting, but this is what my answer should look like. Okay, so sometimes we can have double or triple bonds depending on if they need more electrons or not. A double bond looks like an equal sign and is made of 4 electrons. And a triple bond is, you guessed it, 3 lines, 6 electrons. All right, so let's look at carbon dioxide. So again, we need to decide who's in the middle, the most metallic or the least electronegative. Carbon is further from fluorine, so it is least electronegative. So carbon goes in the middle, oxygen, oxygen. Let's tally up. Carbon has 4 because it's in group 4. There are 2 oxygens. Each of those has 6. So that's 2 times 6 is 12, plus 4 more, 16. Draw in our single bonds first. That used 4 electrons. Then we place those 12 around our outer elements first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've used all of our electrons, which is great. Now let's check our octet. If we look at this oxygen, it has 1, 2, 3, 4, 5, 6, 7, 8 around it. That's happy. Check this oxygen. 1, 2 in the bond, 3, 4, 5, 6, 7, 8. It has 8 as well. That oxygen's happy. Let's check on my carbon. Carbon only has 1, 2, 3, 4. So carbon is not so happy with that. It wants to have 8. So remember, we can dump in and move electrons around. We cannot add any more. If we add more, we're disrupting that 16, and we cannot do that. So remember, what we would do is dump those in and make a double bond on each side. So now I have carbon still in the middle, and then I use 2 electrons, which makes a single bond, to add in. So since I have 2 single bonds on top of each other, it becomes a double bond. And now let's check our octet. My oxygen has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen has 1, 2. Let's fix that. 1, 2, 3, 4, 5, 6, 7, 8. And the carbon here, 1, 2, 3, 4, 5, 6, 7, 8. Everybody is happy for a Lewis diagram that looks like this. We can have triple bonds as well. So we have N and N. 2. Each N has 5 for a total of 10. Drawing my single bond, that takes away 2. 1, 2, 3, 4, 5, 6, 7, 8. you can see that my nitrogen on the left does not have a lot of electrons around it. It only has 4, but my nitrogen on the right has 8. So he's satisfied, but the partner is not. So let's fix that. Can dump that pair in. If I dump that pair in, we're going to get a double bond now. And you can see that the nitrogen on the right-hand side has 1, 2, 3, 4, 5, 6, 7, 8. So still happy. Nitrogen on the left, 1, 2, 3, 4, 5, 6. So this nitrogen is still not happy. So let's dump in another pair. So that's going to give me N, triple bond N, and then each nitrogen still has a lone pair. So let's count these. Let's change our color here. So we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Both of those guys are happy for an answer of N, triple bond N. And remember, it does not matter exactly where that lone pair ends up. So I moved it to the top. It's perfectly fine. All right. We've talked about polyatomic ions. Remember, that means many atom ion. These are the ones that we've talked a lot about. I've given you a list on your summer work of the ones I need you to know at the start of the year. I'm going to skip over these because they're very similar to what we just did. Last things I want to talk to you about is resonance structures. So resonance structures are when there is more than one way to write the same structure. So this is the key here, and I need you to know that. Shifting electrons allows for multiple structures, and those electrons are constantly moving. So just because our carbon dioxide looks like this, it does not mean that these electrons are only ever right here. Electrons in a molecule are constantly zooming all over the place. But what these bonds show us is where they spend most of their time. So we can look at probability maps, and that's what we'll talk about that's what we talked about when we looked at Vesper diagrams, those balloon molecules. So when we look at ozone, which is O3, you can see that there's more than one way to write it. So we initially draw it, and we figure out that it has one single bond on one side and one double bond on the other. But who's to say, and when you drew this the first time, who's to say you didn't put the double bond on the left-hand side? These are completely equal structures. They are both correct. Since they are both correct, we call those resonance structures, because those electrons are moving back and forth. Both of these exist in equal proportions. One of them is not more correct than the other. And that's all I have for you guys as our review for Lewis diagrams and resonance structures.